Sorry. Good evening, friends. This is Dr. I.R. Rajkumar. On behalf of IPS Vadodara, I welcome you for yet another session of Brain on Wednesdays. Dr. Shobha Nair of Bombay Psychiatric Society will join me. Shobha.
Good evening, everybody. Greetings from Bombay Psychiatric Society. And we started this collaboration last year during Ruksheda's tenure. And we are happy that BPS decided to continue with this extremely informative lecture series. And we are, this is the third session since the new year has begun. And today it's none other than one of the program directors himself, who's going to talk and have a series of informative sessions to improve our understanding of the brain. And thank you, Dr. Jalpa, for agreeing to be the chairperson. So that's all from me for now. Enjoy listening and learning. Thank you.
Today's session is Connectomics Basics. Dr. Malay would be speaking on it. And to chair the session is Dr. Jalpa Bhuta, who is a consultant psychiatrist at Bombay, trained at KEM as well as abroad, having 25 years of experience. Jalpa, the floor is yours.
Thank you, sir. So at the outset, I want to thank Dr. Rajkumar and Dr. Shobha Nair for having kindly invited me to be the chairperson, and I feel deeply honored for being considered the same. Basically, today's talk is Connectonomics. So I have a brief idea about this topic because Malay had talked about it in some previous lectures. So when Shobha asked me to be the chairperson, I was more than happy to do so and to support Malay in this and sharing his knowledge. So connectonomics, from whatever I have understood, which is not quite a lot, but I guess it's an exciting new field of neuroscience. And it consists of connectomes, which is the mapping of the neurons. It shows the structural connections and also the functional connections of the neurons and the different neural circuits. And it is a science which shows us how the circuits and the connections work in sync with each other, and they aid in different functions of the brain, and also they help to predict the behaviors of the brain. And it is very exciting to see how it is diagnosed, also how the imaging works, and also its different applications, especially for psychiatric disorders like autism, schizophrenia, and Alzheimer's. So obviously more about it from Dr. Malay. Now, he does not need any kind of introduction. We all know that. But just because I've been asked to do so, he sent me some very, very, very brief details which don't do justice to what all he is. He is one of our godfathers in psychiatry, and every meeting and every conference is incomplete without the presence of our Malay. I call him with pride our Malay because he belongs to Amchi, Mumbai. So he's a consultant psychiatrist in private practice. He's been 12 years as a PG teacher. He's won awards and honors, BPS Silver Jubilee Prize in ANSIPS in January 99, and also Dr. Anil V. Shah Best Paper Award in the 29th ASIPS West Zone in October 1998. He has 12 publications and he's held numerous positions. Example, the honorary president of the BPS, member of IPS UG Education Subcommittee, and he's been the advisor in IPS Biological Psychiatry Subcommittee. His chief areas of interest are neuroscience and genetics. So Malay, the floor is yours. Please begin.
Thank you so much, Dr. Jalpa Bhuta, for those kind words, for introducing me. Thank you, Dr. Rajkumar sir, and Dr. Shobha Nair, current president of the Bombay Psychiatric Society, for continuation of the support that you are giving for our endeavor. So Connectomics, but before I go to Connectomics, a few things that I would kind of start off as a preamble. One is that when we are making an attempt to understand how brain functions, what are the brain functions, how are they integrated, and how does it get kind of translated into the symptoms that we see in our patients daily and what we can do for them. Neuroscience is not one thing. Neuroscience is an evolving attempt to study brain function. So if I tell you at this point in time that I know everything about neuroscience, or neuroscience is now at the end of everything that we know, then it doesn't happen that way. There are many aspects to neuroscience. I have just taken up one topic today, that is connectomics. There are many such aspects. So what I have tried to do is that in the next 6 sessions, so the month of June, July, and August, I'll be addressing the basics of various aspects of neuroscience, so that when we understand that there are these things, when we look at the pathogenesis of disorders and hence how we are going to address the symptoms in our patients, this becomes easily understood. And further down the line, we can, those of us who are interested, those of us who have the means, resources, and the motivation to do research, then these are the various areas that are open to us right now. So for today's topic, Connectomics, the same topic I have presented 2 or 3 times before in different settings. What I have tried to do in Connectomics is give a very brief and a simplified idea of what this is. It's not a complete presentation by any means, but what is going to happen and what I think is going to be helpful to all of us is that when we have understood some things from this, whenever we are describing or discussing pathogenesis of various disorders, we will keep on repeating. One of the things or one of the signs of having understood something well is that first we are able to repeat what we have learned. So, unless things are fixed in our heads, we cannot do anything we cannot go any further. Second is, once we have remembered, we would also understand how things apply. So if I give everything in one shot, it is, but it is going to be so that after 2 or 3 sessions, you would have forgotten everything. So I will be dwelling on the most important points that are of interest from the perspective of clinical psychiatry, means for all of us, irrespective of whether we have read anything in neuroscience before or we are going to read after this, irrespective of that, immaterial. So let's begin. And of course, a few points before I begin. These are, housekeeping arrangements. One is let please everybody be on mute. Second, whatever questions you have, please put it up in the chat box so that we can take it up later on for discussion. Third thing is that there might be questions which I may not be able to answer right now, or I may choose not to answer right now. So please bear with that. And let's start. Okay. Is my screen visible?
Yes, sir, your screen is visible. Open the presentation and make it slideshow.
Fine. Okay. So here is the presentation. We'll start right now. Okay. So what is the basic idea of connectomes, connectomics, connections, and so on? Carl Wernicke was one of the very early scientists and a neurobiologist who thought that schizophrenia might arise from a disruption of the brain's association fibers, that is the white matter. Now, if you look at this statement, which is more than a century old, or maybe more than 1.5 century old, at that point in time, it would have been, kind of a jaw-dropping statement. What is brain? What are the association fibers? When people didn't have any ways and means of looking at all these things apart from dissection, there were no X-rays were there, but then that was not enough to, have a peek at the white matter and so on. CT scans and MRIs were not there. So everything was either X-ray or on the operating table. At that point in time, when somebody would have made such a statement, it would have been really awesome. But well, that was the beginning of some understanding of what might be the brain's contribution to psychiatric illnesses like schizophrenia. Ewlings-Jackson, he mentioned that insanity arose from an imbalance of hierarchically organized neural systems. When we talk of Jackson, we talk about him in the context of seizure disorders and epilepsy. And this is and the ideas that he had given to us about the brain functioning at that time also to some extent hold true right now, in terms of that there are organized neural systems and they are organized in an hierarchy. Means there's a lower order one, there's a middle order one, there's a higher order one, there's a system above that, and so on. And when these systems do not work in proper sync, there's an imbalance. It leads to improper excitation or the spread of the seizure activity and so on. So that was another contribution in terms of the concept of neural psychiatry. With DSM-5, people started thinking, and we are still thinking, that what is going on? I mean, we are just describing symptoms and patterns of symptoms and combinations and this thing and that thing in the last 60, 70 years. And what we see in terms of symptom profiles in patients in real world may not follow the diagnostic pattern at all. Our diagnostic patterns, our diagnostic systems do not decide how treatments are designed. And treatments, when we give, will treat what is there in terms of presentations and something more. So when we are dealing with symptoms, we need to understand what is the underlying cause of symptoms, because if we do not, then we will not be able to formulate treatments, devise new treatments effectively. At that time, there was also the how would we say the rise of the RDoC, that's a research domain criteria, where neural circuits was hypothesized to be a core unit of analysis. Means that when we are looking at any symptom, whether it be a mood symptom or a behavioral symptom or cognitive symptom or whatever, the unit means the basic cause of that symptom will be somewhere in a circuit. Now, what are these circuits? Different neural circuits basically would mean how different neurons come together. So the circuits can be microcircuits, which could be less than or equal to 1 micrometer. Mesocircuits, that would be 1 micrometer to 1 millimeter in size, and macro would be more than 1 millimeter. So this is the scale of the circuits that are important. So microcircuit would mean, let's say, a single synapse, small micrometer, that kind of a thing, or a group of synapses. Meso would be something like what we see in the cerebral cortex, or in terms of the GABA glutamate circuits, which are mutually acting on each other, that kind of a circuit. And macro are the bigger ones, more than 1 millimeter. That would mean, this scale would mean different or adjacent areas of the brain, how they connect with each other. Now, when we map and model the circuit level dysfunction, we can kind of pinpoint pathological systems. Now, these models help us to identify the essential mechanisms to explain a set of empirical findings. Our empirical findings are the symptoms. We have at the moment no single diagnostic test to decide if somebody has got a depressive disorder or an anxiety disorder. It is symptoms, the phenotypical presentation. These are empirical, because we cannot really give a fixed objective value to that, like a blood test or any other biochemical parameter. And this kind of the approach of looking at symptoms, this circuit level dysfunction, can help us to test and generate hypotheses in a formally rigorous way, because now we have identified that this seems to be involved. We can have a hypothesis, we can compare, and we can study it in a more rigorous way, rather than just a group of symptoms, DSM-5 schizophrenia, this works or this doesn't work. So what is a connectome? Connectome is a large-scale brain network. So one one group of neurons would be a connection. Now, if we have multiple connections in an individual, it would be called as a large-scale brain network or a connectome. Like we have genes, and all the genes taken together in an individual is a genome. So that's a connectome. Now, when we look at, or rather when we study connectomes, or there are papers on connectomes, we need to be familiar with certain important nomenclature. There's a whole range of things, but again, if I start talking about them, it will be like a dictionary. So the most important ones are two: the nodes and the edges. What is a node? Node is a represent imaging voxel or region of interest. Now, for example, we know that let's say verbal memory is stored in the hippocampus. So whenever we are looking at memory function in various psychiatric or neurological disorders, or in general, then the area of interest would be the hippocampus, for example. So this becomes a region of interest, ROI. And let's say we use an MRI. We use a high definition MRI, or we use an fMRI, or we use a diffusion tensor imaging. This will be where we will focus on. So this imaging voxels, imaging volumes, this will become a node. Means the most important aspects of memory function are located here. So that becomes a node. So node is structurally important, functionally important, most important in the whole network, and most important for imaging or whatever analysis we want to do. So that's a node. And what is an edge? So when we are talking of networks, a network cannot be a single neuron. It has to be at least two, more than two, or several hundreds. So when we are looking at a connectome or a connection, for complex functions, we have multiple nodes. So again, when we look at memory systems, yes, verbal memory is hippocampus. But when there is the element of anxiety or fear added, we get amygdala, which comes in, and this whole thing then is labeled as emotional memory. So for emotional memory, we have got two nodes, let's say hippocampus and the amygdala. Both of them are important areas anatomically, and also because functionally they are connected to each other and are regions of interest. Now, when we have two nodes, two important areas, they will be connected. So if we look at it like a simple diagram, a node is like a dot. So we have one node hippocampus, we have one node amygdala, and then there is a line which connects. So this line which connects the nodes is called as an edge. So this edge can represent structural connectivity. Now, hippocampus and amygdala are very closely not only located, but they will have same connectivity by white matter. And also in the same activity, they are connected. So there's also functional connectivity. Now, how do we measure that? It is measured by different strategies. So there are different ways of assessing connectivity. The two most important things are functional MRI, means we give a task to a patient when the patient is an MRI scanner. And when he's or she is doing that task, we see the oxygenation or deoxygenation levels in the area of interest, see how well it lights up, see what all light up, and see the whole pathway. So this becomes a functional assessment. We can also do a diffusion tensor imaging, which will look at white matter connectivity. So when areas are close by, when this, let's say hippocampus and amygdala are close by, and we can see their connectivity in terms of the axons or the white matter, then we use diffusion tensor imaging or DTI. So nodes, important areas, edges is their connectivity, and different strategies or different ways of looking at it. Now, all this will be seen as images, but when we are discussing, it is a graph model. So it will be in the form of graphs, because there's a lot of statistical jugglery that is involved in understanding the probability of connectivity, how significant it is, and so on and so forth. So what is this functional connectivity? Well, if we want to look at a very specific definition, then this is the definition. It is a statistical temporal dependencies as demonstrated by synchronous blood oxygen level dependent neural activity over the distributed brain areas. Plain and simple, when a task is given to a patient in an MRI, what areas light up at the same time? This is functional connectivity. Or one area lights up and then another area lights up for that activity that is given, that is functional connectivity. What is structural connectivity? Is diffusion MRI tracer traced white matter fiber tracks. So when we are looking at both this functional as well as structure, we will see areas lighting up, and with diffusion tensor imaging, we can see the whole pathway and see what is happening in terms of structure, not in terms of function. So we will look at things like fractional anisotropy, means what is the conductivity of water along the pathway, and so on and so forth. So this will give us an idea whether these areas of interest, these nodes, are functionally connected and or structurally connected. Now, when there is a network, there are various terms apart from this structural and functional connectivity and nodes and edges. There are certain terms. There are many terms, of which these 3 or 4 are very important. One is presence of hubs. Second one is small worldness. Third is modular structure, and fourth is rich club structures. We will have two lines about each. But this is basically how we will begin to understand the connectomes, or how these connections happen and work. So this is again a simpler diagram. So these green ones are the nodes. For example, these are the different regions of interest. So each is a node. What is a node? It is one area of the brain which is considered very important from a certain function. Now, when nodes, this is one node, this is another node. So now for a function, now if you look at this, this is prefrontal area. So let's say we are dealing with cognition or thinking. So let's say this, they work together. So these 3 will form a network of 3 nodes, 3 important areas, and they can be connected in many ways. So this can be connected to this, to this, to this. Okay. These are the edges. What are the edges? The fibers or the function which connects this nodes. So these are the edges. If you look at a complex network, so let's say 1, 2, 3, 4, 5. There are 5 nodes. Now these 5 nodes can be connected in many ways. It can be this, or this, or this, or this, and so many. So we will have nodes and we will have multiple edges. So functional connectivity would mean that given a task, let's say this area and this area light up on fMRI at the same time, or let's say with a very small gap between them, time frame gap between them. This is functional connectivity. And structure, by we will look at the how the white matter tracks appear on a diffusion tensor scan, and that is structural connectivity. So what happens is, with this kind of an approach, we move from discrete regions to interactions between regions. Now, why is this important? We were given, I mean, all of us, at least I would believe that those who have studied anatomy about 25, 30 years plus, before 2025, we were given to believe, and we have always learned brain this way, that different regions of the brain are important for different things. So let's say we have Broca's area. Broca's area is for motor speech, but it is not only Broca's area which is important for motor speech output. Broca's area has to be connected to different parts of the brain, both on the same side and the opposite side, to get a proper input so that it can have a proper output. But for us, that is important. So it's like a dot in the whole brain, which is important. No, it is not important. But if you look at the network aspect of this, it becomes a prominent node. Because if that is damaged, if there is a left-sided stroke and Broca's area is damaged, the person is going to land up with maybe complete expressive aphasia or Broca's aphasia. Okay. Now, what this means is that when we are looking at networks, we are not focused on one region. We are looking at different regions of the brain and how they interact, and not different regions no, we are not looking at temporal, parietal, and frontal. We are looking at some part of frontal. We are looking at some part of parietal. We are looking at some part of temporal, and how this together, let's say, becomes important in speech production. So it is not only regions or interaction between regions, but it is an interaction between specific parts of different regions of the brain. Now, what is also understood is that pathology tends to concentrate in hub regions of the brain. Now, this is again a new one. We have talked of nodes and edges, but what is a hub? Hub would be, again, let's say if we look at the memory issue, we talked about hippocampus, we talked about amygdala, we talked about verbal memory, we talked about emotional memory. So for memory, this whole system of these two important nodes, hippocampus and amygdala, becomes a hub. Means there are two nodes in this, but these two are the most important in the thing. So these are hub nodes. So hub nodes are highly connected. So one in a, it's like this, that we take any organization. Let's say we take a hypothetical psychiatric society. There would be a president, there will be a secretary, there will be a treasurer, and so many people. Now, when we look at the most important person who is going to take decisions, it's the head or the president. So he becomes a node if we look at connectomic terms. Also important are the president or the secretary and treasurer, because they've got the most important work profiles. But the whole organization runs not because of all these individual people, but together. So these three people, these three nodes become the hub. Okay, so something like that. So hub nodes are highly connected and topographically central elements of a network. They are vital in supporting network communication, because if anything happens to any one of these, the whole network communication can go awry. And this will influence and be influenced by many other network nodes. So these three people in an organization will communicate with similar people in other organizations. They will also get information from other organizations from the same people. So influence and getting influence. But a disease or dysfunction within a hub region. So if this main hippocampus and amygdala get involved in any disease process, it can be anything, degenerative, vascular, developmental, infective, anything. But if a node is getting involved, if a hub is getting involved, then the disease will spread along the edges. Now, this becomes important because this is the vulnerability in a network. For example, we know that clinically, the different types of dementias, if roughly are cortical and subcortical. What does this mean? That some dementias will start the degenerative process in the cortical areas. Some dementias, they will start with the degenerative process in the subcortical regions, the basal ganglia, the midbrain, and so on. But if you see these patients, after let's say 10 years of the degenerative process, they will all appear alike, because whether the degenerative process starts in the cortex or whether it starts in the subcortical areas, finally, over a period of time, sooner or later, almost the whole of the brain, whether it is cortex, whether it is midbrain, whether it is brainstem, everything gets involved. Means the degeneration spreads. And for each of these dementias, wherever they originate, the degeneration spreads. Let's say subcortical to so it will spread up on sides and down. If it's cortical, again throughout the cortex and below. Means wherever there are these hubs. So let's say when we talk of a dementia, we talk of memory, for example. So we look at hippocampus. So there would be areas, let's say dementia starts, the degenerative process starts in the hippocampus. Now this is an important area because it's a node. Along with amygdala, it forms the hub for memory consolidation and things like that. So if any degeneration starts there, then it is going to spread everywhere, which is connected densely to this hub area. So it can proceed to cortex, it can proceed to thalamus, it can proceed to brainstem, right? So disease or dysfunction within a hub region can rapidly spread to other connected areas and vice versa. So any region in a network, if it's hub, then it spreads fast, but anything that is there in any other part of this whole complex can also spread to others. Hub nodes of the human connectome are generally located in regions of association cortex, subcortical nuclei, such as thalamus and striatum. Means for human beings, people have identified that the most important nodes and hubs are in these areas: association cortex, subcortical nuclei, such as thalamus and striatum. Now, if this is actually very logical, because association cortex has to do a lot of, has to gather information from many areas and kind of synthesize, analyze, label, and then send it for further action. So the activity has to be located in very discrete areas, but very specific areas, and which should be densely connected so that the to and fro of information is easy. Those small few other terms that are important is small world organization. Now, small world organization means what? That for a function, for some brain function, there are multiple hubs. Now, these hubs are small areas which are doing intensive work, which are intricately connected with one another. So what happens is any task that organization takes up is pretty quick, pretty efficient, and pretty accurate. This is called as a small world organization. Now, the best example that I can give, which is non-psychiatry, non-biological, is that all of us use laptops, all of us use mobile phones. Now, there is, in all these electronic equipments, there is a processor. Now, what does this processor do? Anything that we put in, it is going to analyze, it is going to calculate, and it is going to give us an output. Now, each of these processors is not one entity. In a processor, there are cores. We have got 8 cores, 10 cores, 12 cores, depending on the number of cores. What does this mean? That if I give my laptop a complex task, depending on what kind of task is there, let's say the maximum capacity in my laptop is 10 cores. 4 will get activated. So instead of the whole processor working and taking up a lot of energy and time, this 4 will get activated. They will do the work quickly, efficiently, and in a fraction of a time, very efficiently, for an output. So this is called as small world organization. Second one is modularity, means a network does very specific thing. So let's say one of the cognitive things that our brain does is labeling. So let's say the label is good or bad. For example, very simple terms I'm using, good or bad. Now, this label of good or bad, okay, the lower brain structures are going to view it as threat or no threat. But as the assessment goes higher up, it will be good or bad with a value. So this good or bad, let's say there is one network which does that. It will do that only. But it will get connected with other things. Let's say it gets connected with motor activity, or it gets connected with emotional regulation. This network is only going to do good or bad labeling. So this is modular. And rich club structure. Rich club structure means the most important hubs in the brain, they are densely interconnected. We'll see that what it means. Rich club structure means, let's say there are 4 important hubs in the brain, 5 important hubs. These are not only connected once, but they are connected 2 times, 3 times, so that information flow is very fast, decision making is very fast, assessments are very fast, and the output is very fast. The more rich club structure is present in a brain, the brain is healthy and free from disease. Meaning, disorders which are chronic in nature, like psychosis or mood disorders, people have found that in their brain, right from development till the onset of illness and beyond, the rich club structure is not that great. Okay. Then there are other terms, which is integration, means how information is integrated, how working is integrated, efficiency of global information transfer, clustering coefficient, means in a small given area, how many clusters are there, length of a network. Very complex, lengthy network means the processing is slow, output is slow. When we look at papers on connectomics, we will come across some graphs like this, directed graph or undirected graph. But basically, it means how the information is flowing. Now, if we look at a directed graph, we get an idea. This thicker areas is how this process is working. This is a stable thing. So maybe in a resting brain, when no conscious activity is happening, something like this. So basically, when connectomics is expressed, it is in terms of images, of course. So one we saw was an fMRI. The second we saw was a diffusion tensor imaging. So we'll have the images and we'll have graphs like this. So we know how the information is flowing. Now, why it is important? Why it is important is because, let's say, if you look at the thick arrow here and the thin arrow here. Now this, if there is a problem here, we need to understand that many times the other ones, the other parts can take over. So this network will remain efficient. But if it's really important and it's damaged and this is a problem, not well developed or not able to take over, then there is a deficit. Now, how we are going to correct this deficit is our headache. Whether we are looking at psychiatry, whether we are looking at neurology, or whether we are looking at anything else. So again, a network is expressed in terms of, we looked at all these ones. We looked at small world, modularity, rich club. So, this is something like multiple networks which are connected to each other. And this is the flow of information. Okay. So how they are connected, what they are doing. So this is how a network is going to be represented graphically. People have also, once we understand this thing, then as I mentioned that there is a human genome, people have, kind of worked out the connectome of the human beings. So, it's a very, it looks like a pin cushion. But if we, this will be on the YouTube, if you can actually expand or zoom in, we will see that each of these balls, this pink colored ball is a node. And there are multiple connections between nodes. So all this fine lace-like, lattice-like white thing is the edge. So we have the nodes, we have the edges, and they have given the names and areas and things like that. So this is how functionally the entire human brain seems to be connected. Now, this was a paper, this is about 4 or 5 years back. So as we understand more, there will be added complexity to all these things. But this is the human connectome. Another way of, once we it's like when we understand a concept, when we have some technology, then it's like a new toy. It's like a new phone that comes with some additional technology every year. So, 10 years, let's say in 2012, 13, 14, 10 years back, the cameras were not so good. Now the cameras are so good in phones that you do not need any other camera even to, make a full movie. So as technology advances, as we become more knowledgeable about what we are doing, we add other things also. Now, what is this? This circle basically gives the various areas. So pons, medulla, cerebral cortex, cerebellar nuclei, isocortex. Now, this is basically an experimental model from a rat or a mouse. And these different areas of the brain are represented in a circle. And all these lines, the yellow ones, orange ones, red ones, yellow ones, orange ones, red ones, they show us how connections happen. So for example, we have got a connection between pons and medulla. So this is how connections are expressed. But what it also shows us is this. Now, this is a complex, it's a combined model of how connectivity happens with how certain genes are expressed. Now, what is the idea? The idea is this, that genes determine, one, what it determines, how and at what speed the development of the brain is going to happen. Meaning, how well the cells are going to divide, move, so migrate, go to their final destination, connect with each other, specialize in function, okay, and get influenced by other systems. So roughly, this is what genes do. So genes will kind of lay down a map for development. Now, what people have understood is that different areas of the brain, especially when there are different functions, there are different kinds of genes involved. There will be structural genes, means genes which will decide how the cells are going to connect, to genes that decide chemical function of a cell or a neuron. So the point here is that not only it shows us how the different areas of the brain get connected, but what kind of gene expression is there. So what it is trying to tell us is that, let's say, isocortex here and cortical subplate, certain genes are highly expressed. Now, when we have a model like this, and we can superimpose some findings of this on the human development, we can understand that, let's say, certain genes which are highly expressed in the connectivity of isocortex and cortical subplate or hippocampal formation, if they are poorly functioning or not expressed, then this connectivity, which is nice and red, means good, will be something like orange or light yellow. Means there is going to be a deficit in function, even though structurally it may look same. The functioning of the network is problematic because genetically there is an impairment. So once we understand connectomics, there are studies which also kind of correlate the expression of genes in certain areas with how the connectivity proceeds. Now, these are some of the basics of connectomics. It is mandatory that when we talk of connectomics, we talk also of certain important networks, because the study of connectomics, or rather study of these networks, is parallel. So we understand connectomics, but we also understand these major networks. Major networks, I am just going to mention a few, 2 or 3. But what I am going to not mention are the many ones which we will probably have an opportunity to discuss later, because they are maybe disorder specific or they do not necessarily come under the title of major ones. So first one is the default mode network, DMN. So this was the first network which was identified. Okay, it was supposed to be stable, inactive, but dynamic. Now, first we can understand, but stable, inactive, dynamic, these are all very confusing terms, because if one is stable, how can one be dynamic? If one is stable or dynamic, how can one be inactive? So this, the moment we understood the default mode network, we get confused because it functions like this, all 3 of them, stable, inactive, and dynamic. So what is this network? So this is an fMRI picture of what this network consists of. So basically, this is the right hemisphere, RH, left hemisphere. This is the lateral aspect, this is the medial aspect. So we have the temporoparietal junction, we have the dorsomedial, ventromedial prefrontal cortex, precuneus, posterior cingulate cortex, okay, medial temporal gyrus, middle frontal gyrus, inferior parietal lobule. Means if you forget the names, even you just look at the lighted areas. So default mode network in the cerebral cortex extends from prefrontal, temporal, parietal, dorsal. So all important lobes of the brain, east, west, north, south, everything is involved in the default mode network in the cerebral cortex. But when we studied it in depth, it's not only the cortex, but if we look at it, structures which are subcortical, thalamus, amygdala, midbrain, temporoparietal junction, cerebellar hemisphere, cerebellar tonsil. So right from cortex to the cerebellum, it's a very intricate network. The most important areas, so on this scale, anteromedial PFC, ventromedial PFC, then DPFC, posterior central. So these big ones are the important nodes. But the red ones, these ones, they become very important in functioning. So this becomes a hub. Okay. So this is a default mode network. Includes lots of areas, cortex, subcortex, up to the cerebellum. Okay. So again, these are the areas that are involved. But this is the structural connectivity aspect. So these are the white matter tracks which are connecting all the areas. So a better part of the corpus callosum is involved here. Then we have the long fascicles. We have this is the limbic, this is the fornix, so this is the limbic cortex, and so on and so forth. So the impression that it gives us is that, you know, the whole brain seems to be the default mode network, both structurally and functionally. This is the same thing that we talked about in that. So, but here there is no genetics involved. These are the different areas of the brain, how well they connect with each other. So the darker it is, the more important it is. Okay. And then that area, this area becomes the hub with nodes. These lighter gray ones contribute, but they are not the important parts of the hub. So what is the importance of the hub? I'll repeat here. One is that they are the most important parts of a network. They run the whole network. They interact with other networks. If there is a disease in the hubs, it spreads everywhere. This is what the hub is. What does it do? There are three main aspects. There were three main aspects. Again, I'm not going to get into the DMN too much right now. It's not what we are talking about. We'll take another, we'll take it other time, the remaining aspects. So what is important? The neurological basis of the self, thinking about others, remembering the past and thinking about the future. So what are the essential activities? Now, the activities, one is giving a label of self, whether it is experience, whether it is action, whether it is memory, whether it is thoughts, whether it is emotions, identity. So this kind of a label is given by the default mode network. Now, once the self part is aware, kind of clear, then it is others. What do others think? What might others be feeling? What is others' impression about me? What the other is doing is, a judgment of what the other is doing, right, not right, social relations. So everything about others. So neurological basis of the self, thinking about the others, two important things. So self and others. And third is remembering the past. So basically it can lock into the memories. Depending on the memory, it can imagine the future. Now, imagine the future is basically remembering the past, story comprehension, episodic memory. All this is important for high-level prediction error representation. Means that whatever my memory is, whatever my thoughts are, now if this is integrated, I can have a prediction about what can happen. This is actually a true so-called human activity. This seems to be automatic. This requires a lot of development of all these things. Then only we can have high-level prediction error representation. Means, what is a prediction error? No prediction is 100% complete. But there is a prediction error. Prediction error means there's a margin. That this, we never say that I am going to be, it's always hum honge kamyab. It never is like I am going to be 60% successful or 93% successful. But we are able to make some kind of a decision within these margins. We can call it whatever, we hum honge 100% kamyab, but that never happens. So how prediction error is taken into account, that this is the chance of my success, it will vary. It will vary from time to time. It will vary from person to person. It will vary depending on the situation for the same task. But these complex calculations happen because of the default mode network, because it integrates everything. So when we have these three things, self, others, and remembering the past and predictions, then we have got three subsystems. So information about the self has got these functional hubs: posterior cingulate and precuneus, medial prefrontal, angular gyrus, three main ones. Thinking about the others is this plus this others. Autobiographical memories, posterior cingulate cortex, medial prefrontal cortex, and angular gyrus, plus hippocampus, and so on. So what happens is that, again, going back to the connectomic basics, hubs. These are the most important. These three are the most important hubs in the default mode network, because they'll keep on coming again and again. Plus an integration with others for specific tasks. So this is how the DMN is organized. How does it function? So default mode network was supposed to be the quiet, silent worker. Means when I am not doing anything actively, okay, this is what is working. The moment I do some task voluntarily, means, okay, now I decide that I'm going to watch TV. So the moment I decide, this is the salience network. So salience is, okay, I want to do this. This shuts down, other areas get lighted up for activity. So this was supposed to be inactive. So the point was that this was the first network. Here it is. This was the first network that we kind of identified. It is supposed to be inactive. Inactive means when I am inactive, not the brain, I'm not doing anything consciously, this is active. So basically it's an inactive part or functioning of the brain. It is stable because there are so many areas involved. But now we understand, again, we are not going into it, that it is not just that. Even when we are consciously doing something in the background, integration of information to a response is done by the DMN. So basically, traditionally, the default mode network is an anti-correlation network. Means if this is active, central executive or what the output is consciously will not happen. And if this is active, this is going to be shut down. And what is the switch? The switch is the salience network. Again, there is a genetic component that is involved in the development of the default mode network. There are certain genes which are the human evolutionary genes, which over time have kind of, they involve a lot of things, neuronal enhancers, biological processes. These genes are important because over years or millions of years, they've evolved to give us what the DMN is. We'll just leave it at that. Okay. Now, if you look at that diagram, so this, all the red ones are the nodes and the black lines are the edges. These are all the areas which are kind of top to bottom, the areas which are involved in that complex diagram in the default mode network. When we are born, all the areas are there, but the connections are not there. You will see many areas which are not connected to one another. But as we become older, not only the lines become darker, but this whole becomes very complex. It becomes a true network. Areas are the same. Connections are also there. But if you look at this black line and this black line, this is darker. If you look at this one and you look at the same one, it is darker. So the network evolves. How does it evolve? One is the inbuilt developmental processes that are happening. Second one is the interaction with the environmental stimuli, because learning happens. So this becomes more and more complex. So if you see same connections, but darker and darker, so this is what is called as a rich club network. One of the components that we saw, or one of the qualities that we saw in when we talked of the basic connectomics, a rich club. Rich club means what? This is a poor club, means everything is there, but it's not connected. And this is richly connected to one another. How do we modulate? So medications can modulate, TMS, vagal nerve stimulation. So whatever are the existing modalities of treatment that we have can modulate many activities. It's a complete list. It's not a complete list. Is it an accurate list? It is not an accurate list. Does it happen all the time? Not necessarily. But these are the approaches we have now, because once we understand that, okay, this could be the processes behind a disorder and the disorder is getting better. So the modalities that we use will be having a certain effect on all these things. Forget this part. But people have identified DMN dysfunction in Alzheimer's, schizophrenia, temporal lobe epilepsy, depressive disorders, and so on. Now, if the whole brain is involved, let's say we look at this one, if the whole brain is involved It is important as to which network is involved more, which part is involved more, and we are going to get a symptom or a phenotypic presentation of a certain something. The second important network is the salience. Salience is basically, it means what catches my attention. There are so many things happening all the time around me. Okay. Right now, when I'm talking to you, my phone is next to me, and there are certain, even if I have kept the phone on its face, there will be certain beep sounds, means there is some message has come or some notification has come. Now I have to focus on what I'm talking. So the focus on what I'm doing is the salience, because this is what attracts my attention. I'm able to keep this, everything else aside. So salience. Now salience is a simpler network. Okay, but what does salience do? So salience, as I mentioned previously, it is a switch between default mode and the central executive network. So what does it do? Main important areas are frontal insular cortex and anterior cingulate cortex. Two main areas. And what do they do? This insula is on the surface between three parts of the brain: frontal, temporal, and parietal. So here it is. Now, what is the most important function of the frontal insular cortex? It gathers all the information that is coming from the various body systems. So whether it is sensory, proprioception, everything that is coming, that is happening in the body, inside the body, the sensations that are produced, the sensory input that is generated, everything comes from the brainstem through the thalamus to the frontal insular cortex. It interacts. So this is the hub: frontal insular cortex and anterior cingulate. Now, once it reaches anterior cingulate cortex, this is a sensation. This is a sensory input. This gets converted into some kind of an output. What output? The output can be autonomic. So if I've got, let's say, not feeling well, some stomach upset, many things will happen. I can have anxiety-like symptoms. I can not feel okay. I can have disease or illness behaviors which might look like anxiety or depression. So whatever is the output, that happens via anterior cingulate cortex. So this is pretty simple. Compared to the default mode network, which is the length, breadth, top, bottom, sides, everything in the brain, this is very simple. Frontal insular cortex and anterior cingulate cortex. So when all the stimuli are coming, so internal stimuli coming from here, now anterior cingulate cortex is here, near the prefrontal cortex, near the medial prefrontal cortex. Medial prefrontal cortex gets information which is emotional in nature, which is anxiety or threat in nature, which is external cues. So this gets kind of mixed together. So sometimes we say, no, that I have got a pit in my stomach, which is nothing to do with any physiological abnormality, but basically it is threat perception, which is manifesting as a GI kind of symptom. So this is what is happening. So an integration of internal stimuli, external stimuli, and an action produced is salience. But salience is how it is working. This is the mechanism. But what does salience mean? That's something in the environment. So something which is taken from the internal environment or the external environment is given a label of being interesting or worthy of focus, and this whole network gets activated. So, for example, a little bit of stomach upset. I've eaten pani puri today, so some stomach upset tomorrow, not feeling okay. Now, this, if it becomes a salient input, gets integrated with emotional, no, something is wrong. I'm not sure whether it is okay. Do I need to visit a gastroenterologist? Will it be something chronic? Will it settle down? My grandfather had CA rectum, CA colon. Will it happen to me? And so on and so forth. So this is salience. Why? Because of all the input that is happening, internal, external, this is salience. The network picks up that something, okay, and then we have an output, which is here. So this is salience network. Like the previous one, DMN, as we become older, this various areas, the primary, these hubs also get connected with others. They are there, but they become more tightly connected. So evolution or developmental evolution of the network. Now, again, what is important here is that all the other areas, now these are the hubs, but if you look at other areas, they would also be some part of the default mode network. Point is, I already mentioned before that when we are looking at connectomics, we are not looking at regions of the brain, but we are looking at parts of regions of the brain. So we will have some part of the temporal lobe or this is the opercular part of the temporal lobe, which is involved in the salience network, but some other anterior temporal gyrus will be involved in the default mode network. So we are not talking of regions, we are talking of components of those regions which are involved in different networks. What also has been found is that in the salient areas, in the salience network areas, we have got a specific VEN, von Economo neurons. Now, what is the importance of this? These von Economo neurons are kind of involved at first
स्टंप लाके दिए कहाँ गए स्टंप
in behavioral variant FTD.
उन्होंने पता नहीं कहाँ पे कर दी हम सारे के सारे 4 रन चाहिए
Hello.
So
go ahead.
behavior,
Please
behavior.
mute yourself. Mute yourself. Someone disturbing.
So when
Sir,
we
I
have,
done that. Go ahead.
so when we have behavior variant FTD and the degeneration pattern, which is observed, seems to start from these two areas. Which two areas? These two areas. Why? Because a certain group of specific neurons, von Economo neurons, are kind of densely located here, and the degenerative process seems to start there. Like in Parkinson's, in the midbrain, in the substantia nigra, the degeneration starts there. So something like this is being looked at. The third important one is the central executive network or lateral frontoparietal network. Basically, it's the executive. So what are the components? Ventral is this one, okay? Inferior frontal gyrus, middle frontal gyrus, temporoparietal junction. These are the main areas, right? So they become the hub, and these are the associated areas. So again, how does it get there? We have seen this again. Inactive, in double quotes, brain is the default mode network. Salience activates the central executive network. So this is the switch. When this is active, default mode network was supposed to be going to sleep, but it doesn't. And that's why it is called as anti-correlation. So what are the functions? Central executive is everything. So whatever is our output from wherever, in whatever modality. So whether it is reaching, grasping, attention, mental rotation, working memory, cognitive tasks, okay, these are supposed to be higher order, very higher order functions. So any sensory input, we talked at the salience network, which gets integrated with whatever is being processed by the default mode network. So that is self, others, memory and prediction, along with incoming stimuli, is going to lead to an output, which can be any of this. Reaching, grasping is motor. Saccades is eye movement tracking. Spatial attention is focusing on one. Mental rotation is how we are going to look at things. Working memory. So all cognitive tasks. So cognitive task is not only thinking or memory. Cognitive task is any output. Any output which comes from any part of the brain because of a processing and a combination of salience networks and salience network and default mode network is cognitive. So this is central executive network. Okay. So rule-based problem solving, actively maintaining and manipulating information in working memory, decision making, inhibition, task switching. Okay, everything is central executive network. Development we know, so we are not getting into it. But if you look finely at what is this cognitive output, spatial orientation 5 months, working memory span starts developing at 6 months, mental representation of objects 7 months, and so on and so forth. Connectomics in pathology, here I'll just give one example the last few minutes. Let's look at schizophrenia. So what have people found in different studies? Structurally, okay, so we have structural connectivity, we have functional connectivity. So what is structural connectivity? More separate, okay. So all those areas are there, but they are not working together. They are more segregated, less integrated. So the global efficiency of information processing and the output is not really great. And distributed set of brain nodes. Functional is randomized tendency. So increase global integration, but decrease local segregation. And less clustered. So sometimes the output is okay, most of the times the output is not okay. The output may not be in sync with the sensory input and so on. A less hub-dominated configuration. Okay, and that is what is meant by rich club. So this is the rich club. With this we have seen, I have tried to explain to you when we looked at the development from childhood to adulthood in default mode network. Okay, these red ones are the main areas. And this whole red thing, it's densely connected with each other and everywhere. So this is a rich club. But when we have schizophrenia, the connectivity seems to be much less. So this doesn't work. Areas are there, they are connected, but the connections are not good enough. They will not work together. That's why the output is not very good. The output is not very efficient and so on. Also, what people have found out, and like we know, even if we have not understood anything about connectomics, is that there is a symptomatic overlay. There are transdiagnostic symptoms or phenotypes. So there will be certain symptoms, let's say anhedonia, apathy in depression, some kind of amotivation in ADHD, negative symptoms in schizophrenia. So there's going to be an overlap in networks. So there's going to be overlap in symptoms. So this is probably what the diagram is telling us. So what is the good part about connectomics? It gives us an insight into pathophysiological mechanisms. It can also make us more knowledgeable about what are the mechanisms underlying various treatments, potential therapeutic targets. But what is challenging? This is technology dependent. So with current technology, we have understood this much. Now, 20 years down the line, if the technology is much better, much improved, newer things, we're able to integrate different models of, I showed you that circle diagram in the rat where they have studied not only the connectomic presentation, but even the genetics of various areas. So when we have more complex tools, more technological advances, whatever we are discussing right now might be proven completely wrong. But this is what the state of affairs is at the moment. Another thing is that whatever studies are done, okay, these are, technologically challenging studies, statistically challenging studies. So they're done in smaller patient groups. Many of these are not replicable very well. So we need, again, the same kind of thing, bigger studies, more number of people involved. So large sizes. Again, when we're looking at a connectome, or let's say a simple connection, there are so many things involved, right? From genetics to anatomy, to the chemistry, to the electrical activity, and so on and so forth. So there are so many things that we have to study. So, and of course, there are environmental effects, again, age, disease progression, how treatments, I mean, when they work, how do they have an effect on the connectome? Everything is, this whole field is maybe about 25 years. So if psychiatry is a young field, this is kind of still infant. So let us take it from here. We are going to have more information. Let's see if it works in our favor or it just throws everything out of the window. Ongoing studies, human connectome project for early psychosis. 400 subjects, 3 Tesla MRI. So they are looking at structure basically, or an fMRI, that's all. Then we have perturbation of the treatment of resistant depression connectome. therapy wise. Okay, again, it's an imaging study. So, well, let's see when this, because these studies were supposed to get done in 2021, but they are ongoing. And when we have any papers which are coming from their centers, will be all the more wiser. So thank you, and over to you, Jalpa.
Sorry about that. Yeah, thank you, Malay. That was a fantastic talk, and it was a learning experience. So we got an in-depth knowledge of connectomics, starting with what is a connectome, what are hubs and modes and edges, and of course how they are linked to the genome. And then the bit that I really loved was also about the DMN and the salience network and also the central executive network. So that was very fascinating to know about all this and the potential application that we can later on do in the future. So thank you for this very, very complete talk, Malay, and wishing to hear many more talks from you in the same way. For the audience, I think we are ready to take questions. So far, I've got a couple of questions here. One is by Dr. Bhalbhadra Jadeja, and it is how to interpret the aberrant connectivity, that is the sorry, it's not coming clear, hyperconnectivity in psychiatric disorders when the direction of causality is not known. And how do we use this data for differential diagnosis rather than just retrospective classification?
Okay, so the thing is here is that if we get into it, we are jumping too many guns. So first of all, what we would really be interested in is, given a set of symptoms, is our knowledge, I mean, with respect to connectomics, complete? Okay, because when patients tell us something and we understand it as a phenotypic presentation, connectomics is just a very basic thing. There will be a lot of other things, even in that connectomic explanation, which may be necessary. So yes, it is not very, it's difficult to diagnose something on connectomic basis. At the moment, what we are trying to understand is that given a set of symptoms, what is probably happening in a patient. Now, over, let's say, maybe later on, I'm planning to present on what is very important for all of us clinically and for the patient, is this precision medicine in psychiatry. Meaning, what people have done is this, that, I discussed some findings in schizophrenia, for example. Now, what people are going to do when we are trying to be precise in trying to understand, one, the symptoms. Second is, once we have understood the symptom, does it have a predictive value? So, for example, we have understood the connectomic basis of symptom A in a patient. Now, we know that in first degree relatives of any given major psychiatric illness, in first degree relatives, there are less intense or subclinical kind of symptomatology present. Now, what we need to understand in them, are the connectomic changes similar? So in precision medicine, what we are going to take from this is that along with the so many things, precision medicine is not only about connectomics, but is about many aspects. It is about genomics and proteomics and transcriptomics and metabolomics and lipidomics and ABCD XYZ. And when we have this thing, is it a prediction model? So there are studies, and yes, that can give us a direction even before the symptoms are kind of established in an individual, that this kind of a pattern, this kind of a connectomic picture can be predictive of something. So we are not only looking at just the causation of symptoms or the phenotypical presentation in a certain individual, but we are trying to be predictive. So how do we use this data for differential diagnosis is how precision medicine and psychiatry is going to evolve. So as I said that this is just a basic idea. This is an evolving branch. This is an evolving part of neuroscience. It's an interesting one because this is one point where a lot of things will merge together. So when later on, when we are talking of precision medicine, again, we'll come to it. So please remember the question and ask again, and let's see if that is going to answer you better.
Okay, Malay, there's another question from Dr. Usman. The comment is, thank you for summing this complex machine. In everyday formulation, how effectively we can use this knowledge? Are there any limitations or expansions? Any example would be good.
Yeah. So again, as I said, now when we're looking at default mode network, and before we finished the default mode network and went on to the salience network, there was a small table in which 4 disorders were mentioned. Schizophrenia was mentioned, temporal lobe epilepsy was mentioned, Alzheimer's dementia was mentioned, and depression was mentioned. And each of them had certain changes on the extreme right side with regards to default mode network. 2 things are there. One is how we understand default mode network. Is it just an inactive one? As you know, it's an anti-correlation network, or it is something else. So there are more and more papers coming out which are telling us that it is not only inactive. Actively also it does a lot of things. And it's not only involved in these 4 disorders, but it's involved in so many else. So many other disorders also. Maybe not the whole network, but certain components of this. So the limitation is this. The limitation is that a connectomic involvement is not specific for a disorder. It is definitely not specific for any category of disorder. Symptoms, yes. But symptoms for various disorders combine in different permutations and combinations. So at the moment, if I want to have a kind of a, how do we put it, a diagnostic formulation based on connectomics, it is going to be very, very rough. And at the end of that, what are we going to do? The modalities of treatment that we have for modulating the networks are 2 or 3. One is the medication group. Second is the intervention group, which is ECTs and others. Third one is treatments like cognition-based treatments, not CBT, but the cognition-based treatments. So we are using them with the idea that this may bring about changes, maybe short term, maybe long term. We are definitely not sure about it. See, when we are treating, we aim not to only treat symptoms, but we want to modify a disorder also. So when something is being used, is it going to modify a network in the long run? And will that modified network be stable and work normally or near normalcy is a different thing. So we are going to have a lot of limitations. If we base our understanding of symptoms only on this, because this is evolving. This is evolving. So we'll have more information and more,
Okay, there's one more again. Hold on. Yeah. So, Dr. Usman, again, can you formulate how an autistic case has different networks working for it?
Again, autism is not one symptom. It will have symptoms from everywhere. So suppose we have let me put it this way: if we have an intrusive or a default mode network which doesn't shut down as much as it is supposed to be when there is a central executive coming up, so we will have elements of other things coming in. So the cognition, let's say, is not very clear. There will be a lot of noise. There'll be some random memories coming in, some random things happening. Okay. So an overactive default mode network is there. Aberrant salience is there. Now, aberrant salience is not only the hallmark of autism, but it will happen in addiction disorders also, or impulse control disorders also, because salience depends on what is interesting to me, what my brain picks up, and how it processes. And then there will be a lot of central executive network issues in terms of being able to focus, abnormal anxiety, so abnormal activation of the autonomic nervous system, and so on and so forth. So again, the exercise would be that whatever networks we know, is there a component of this or a combination of this in the various symptom presentation? So autism is just a name that is given, but there are so many kinds of symptoms that are there, right from socialization, right from poor empathy development, that is uh, what the others may be thinking, and so on and so forth. So yes. Now, the best part would be that if we are able to see, normally also when we devise treatments for a developmental disorder like ADHD or ASD, we look at symptom profiles and see what we can do. What is medically amenable, what is therapy amenable, what is something else amenable, social skills amenable, and then proceed accordingly. So anyway, we kind of tease out the symptoms that we are going to be addressing. This is my work, this is not my work, this autist will do, or this behavior therapist will do, or something like that. So we do that. Now, when we are adding connectomics as the basis, we are probably becoming more aware of two things. One is what other networks are getting involved and what other modalities we can use. So many times when we are looking at repetitive behaviors or aggressive behaviors, and we add risperidone, it might reduce the salience, but it might not reduce something else. So maybe an SSRI is a better option there. So given what we know about a disorder, our understanding of a disorder, we can kind of build our hypothesis using connectomics, and at the moment, that's about that.
Okay. And Dr. Shobha Nair is asking, hubs are essentially neuronal cell bodies and edges are the axons. Can there be functional connection without structural connections?
Yes, apparently yes. That happens with the default mode network, because there are so many areas involved and they may not be connected. But for a given task, they might light up at the same time. Let me give you an example. When we are reading something, okay, when we are reading something, we are seeing something. Something is in front of us. The moment we start reading, we also start processing things. And some of it also gets added from previous memory. It happens. Okay. So this may not be linked. A default mode network, if you're looking at it, okay, some areas may be linked and some may not be linked. But for a given activity, they are all working together. So the simple answer to Dr. Shobha's question is yes, there can be functional connection without structural connectivity.
So we've come to an end of our questions. Thank you for the enlightening talk, Dr. Malay, and I hand over to Dr. Rajkumar.
Thank you, Dr. Malay. Thank you, Dr. Jalpa. We'll be looking forward for yet another session with you, Dr. Malay, Epigenetics in Psychiatry on the 25th of this month. Till then, goodbye, friends, and good night to all of you.
Good night.
Bye.